First of all, I want to thank you all for joining us here tonight. I'm Pete Eberle with the Colorado Renewable Energy Society, or CRES, and this is our northern chapter NCRES. Anyone here not familiar with CRES? Okay, so I'll go through this few. So CRES and our local chapters provide education, policy advocacy, and community engagement that accelerate Colorado towards a carbon neutral future powered by 100% renewable energy. Founded in 1996, we're a statewide, nonpartisan 501c3 that's supported by our sustaining members, as well as individual donations. You can sign up for our newsletter, event announcements, social media, and become a member or donor at cres-energy.org. Also make sure to visit our YouTube channel where we'll have this, and I think we've got 220 videos with about 1.4 million views. So there's a lot of good information out there. I want to give a special thanks to our gigawatt and megawatt business sponsors, Moss Adams, Hooter Valley Rural Electric Association, Centon Instruments, Kelly Government Solutions, Solaris Energy, Platte River Power Authority, as well as Sandbox Solar, another one of our local members up here. And just a couple quick announcements on upcoming events. On Thursday, April 25th, 2 days from now, at 7 p.m., we will have How to Electrify Your Home and Why You Want to. This will have Eric Wilson of NCRES. It will be down in Golden, Colorado at the Jefferson Unitarian Church. It will be live streamed. So if you go to cres-energy.org, events, you'll be able to register and watch that. There will be a follow-up presentation on Thursday, May 23rd, also starting at 7 p.m., also in Golden, Colorado at the Jefferson Unitarian Church. And this will be home electrification. How much power do you really need? It'll have Sean Lemons, I totally missed his name, formerly of Mitsubishi Heat Pumps, and it's talking about really, your electrical service. A lot of people say, hey, my electrical service is too small, but there are ways to work around that. And then back up here at NCRES on Tuesday, May 28th, we'll have plastics recycling with Plastics to Green, which if anyone knows Ed Van Dyne, he's a serial inventor and startup guy, and he's looking at doing chemical recycling of plastics into ammonia, hydrogen, as well as other chemical feedstocks. May 28th at Eberle Brewing, so we're back at our home place. Again, you can find all of that at cres-energy.org. And without further ado, I will hand it over to Ashwin.
Hey, thank you for hosting and getting this all set up. Yeah. Welcome everyone. Before we talk about me and what we're doing at AtmosZero, I kind of need to know who I'm talking to here. Who's an engineer? Fantastic. Who's here because of heat pumps? All right. Who's here because of the free snacks and drinks provided by? Got it. Thank you for doing that. Appreciate it. And thank you all for your time tonight. I want this to be interactive, so feel free to jump in and tell me to stop talking and ask questions. We're going to also follow this up with a tour of not just the AtmosZero system that we have here. It's an app scale, full industrial scale heat pump based boiler, making steam. Not running right now. But we also have the powerhouse itself, the engine lab that we want to introduce you to if you've never been here before. It's an awesome place. So let me get started. I'm Ashwin Salvi. I'm one of the co-founders and the chief operating officer for AtmosZero. I'm also the global head of business development. It's a startup company. We wear lots of hats that conflict with each other sometimes. But I've got a background in the climate space, the clean energy world, roughly 15, almost 20 years now. And that's anywhere from fundamental research at the lab to commercialization, working at other startups, and even the federal agency, Department of Energy at ARPA-E. So I kind of already went through this before. I did my PhD at University of Michigan. I'm a mechanical engineer 3 times over. Didn't branch out much. But I did a lot of work on thermodynamics and heat transfer. A lot of that is what we're using today in our heat pump-based system. That's what my career's been in. Thermodynamics makes sense to me. It's fantastic. It's what makes the world go round. I also started the Energy Club. So while I had a focus on technical development with my PhD work, I also had this kind of broad perspective of energy and how do we do energy in the world. And that got me thinking, when I finished my degree, what do I do next? Going to fundamental research didn't seem right, but at the time, there's this agency called ARPA-E, Advanced Research Projects Agency in Energy, It's a wing of the Department of Energy that was kind of fairly new. It's kind of this high-risk, high-reward agency. And I went and interviewed for a position there, a fellows position. And it turned out to be just the most incredible career decision that I've ever made in my life. I went from this narrow focus of thermal properties of heat exchanger fouling, right, to this broad range of projects. I was working on fusion, I was working on photovoltaics, electrochemistry, automated vehicles, all this kind of stuff. Right, just completely opened my eyes, not just to the technology side of things, but also the commercialization side of things. Worked with a lot of teams on understanding what is it going to take this thing you've got in your mind and translate that from a lab setting into a commercial product and get that out the door. Fundamentally, what matters is if you don't commercialize something or inspire something that does make it to the market, you're not having the kind of impact you should be having. And that's what really focused my career from this research kind of application into more of a commercialization type of application, right? So that's when I went to a startup that took me out to California called Katie's Power. I'm not sure if anyone's familiar with it. It's a powertrain solution, so high efficiency, low emissions for automotive applications, military, stationary power, that kind of stuff. But I started fundamentally in the lab. I got my hands dirty, testing, understanding how this new kind of idea, this new hardware, how that works. So that when I'm talking to folks like customers, anywhere from the C-suite all the way to ground level engineers, I could talk the full spectrum of commercialization to technology development to fundamental reasons why we have the advantages that we do. And that was super exciting for me because I got really, really hands-on with customers, started putting products in customer hands, getting their feedback as to what the challenges were and what their challenges that we're trying to help them solve are. And that's exactly like what I've focused on, and that's what I love because I want to see making positive impact on the world. That's what brought me to AtmosZero. So I started this company 2 years ago with two of my co-founders. One of them is Ashwin Stark. He's the CEO of the company, and he and I actually worked together at ARPA-E, that Department of Energy agency, almost 10 years ago at this point. Back when we were at ARPA-E, we actually met our third co-founder. We didn't know at the time. We just started this company 2 years ago, right? His name is Todd Vandauer. He's actually a professor here at CSU. His office is one floor above us. At the time when we were at DOE, we funded Todd and his research group to do projects for us. You know, the whole point is DOE gives funding opportunities for folks. They go and build big things, de-risk the technology, the idea itself, and work on commercialization. When we were working with Todd at DOE, we realized that he had access to CSU, Colorado State University, the Powerhouse, and a team here that can build industrial scale things in a very, very short amount of time. When you're building a company, especially a startup, time is not your friend. And certainly you don't have a lot of money either, so time correlates to money to me. We wanted to build things quickly and wanted to build things at industrial relevant scale to the world that we're working on, right? That's why we decided to create a home here at Fort Collins, and in particular with CSU. What we're working on is industrial scale decarbonization, and we're decarbonizing steam. So this is a very not residential focus that you're probably used to in terms of heat pumps. This is the industrial setting, things like manufacturers of food and beverage products, chemicals products, etc., just large industrial settings. And the reason we're focusing on steam is because almost everything in this room has been touched by steam. It is a global energy carrier and a huge, huge amount of energy, primary energy, a lot of CO2 is associated with the generation of steam. So the drinks you're having right now, the snacks that are over there, the clothes you're wearing, the toothpaste that you used this morning, was all impacted by steam. And that's why it's a very important thing to decarbonize, because it's a huge signature of CO2 in the world. So we're focused on delivering low-cost decarbonized solutions for the industrial sector, really replacing today's fossil-fired boilers with an electrified solution that eliminates on-site emissions. That means, boilers today use natural gas or coal or whatever fuel they use. They burn that, make heat, use that to boil water. That's how we make steam. That's how we've made steam for the last 200 years. And that hasn't really changed. What we're doing is creating an electrified approach and making it cost-effective for folks to switch over to a cleaner solution. So eliminating what we call Scope 1 emissions, which are point source emissions, on day one. So it's a quick-to-deploy solution. Perfect timing with the train. So again, steam. Why steam? If you look at the industrial setting, About 50% of the heat in the industrial sector is produced, heat is produced by steam. It's anywhere from 100 degrees Celsius. I'm an engineer, I think in Celsius. I know a lot of you are as well, but I can convert to Fahrenheit if you really want me to. 100 Celsius to 200, 225 Celsius. Just 100, 125 degrees Celsius window, it amounts for 50% of process heat. That means it's actually not that big a window, right? You don't need a solution that has to go all the way to 500 Celsius, all the way down to 100 Celsius. That's a much harder solution to solve for. If you can make something that is in that 100 degree range, you can have an outsized impact on global CO2 because of how much steam is being used in the world. And that's what got us thinking about, all right, if you narrow the window of this 100 degree opportunity, how do we create a product that can be high efficiency, so bring the cost of going to electrification down, as well as a scalable solution so multiple people around the world can buy this thing and have impact globally. That's how we came up with the idea of AtmosZero and the reason that we're based around a heat pump solution. I'll get into all of this in a little bit. But again, in that 100 degree window, we're talking about chemical sectors, food and beverage, so beer, meat packing, etc., pulp and paper, pharmaceuticals, oil and gas, district heating. So CSU has a district steam network that passes steam to buildings for heat. So much of this kind of energy is just in that 100 to 200 Celsius window. Yes?
I have a question, sorry. What about steel? Is it enough to run steel processes?
So steel is certainly much higher temperature. So we're talking about 500 Celsius.
Okay.
There's technologies better suited for that, and actually we'll have a slide on this too. But great question.
Yeah, thanks.
So the power of steam. We already talked about this, 50% of process heat. That's 8% of global CO2, just in the industrial sector. If you start talking about district heating networks, like I mentioned, CSU has the steam network underground. Most universities do. It's the city of New York. In Denver has district heating networks too that go to large multifamily homes, office buildings, same in New York. That goes to 12% of global CO2 is just making steam. Literally burning fuel to make heat, right? So steam drove the Industrial Revolution 180 years ago, and we've been making it exactly the same way since. It's time for a different way of approaching that. So let's work on redefining the boiler room. We talked about this quickly, but if you look at a boiler room today, your general technology is a natural gas or some sort of fossil fuel fired boiler. You burn that, you make CO2, you make NOx emissions, you make a lot of point source emissions at that facility itself. That heat goes to making water into steam. Pretty straightforward, it's gotten us to the luxuries that we have today, but like I mentioned, it's a large source of emissions. If you wanted to decarbonize that today, your only real solution going forward are what we call electric resistant boilers. Think about the electric tea kettle you have at home. The little water boiling thing that you put the button and they start making steam. It's just on a much bigger scale. That's what an electric resistant or electrode boilers are. Those are your main solutions to decarbonize. In fact, there's a number of companies out there in the world that have already started deploying this. If anyone here is a Bullet Bourbon fan, Diageo, the makers of Bullet Bourbon in Kentucky, they installed electrode boilers thinking it's a great bourbon. They installed electric boilers because they're trying to decarbonize the way they make steam. The only challenge here is now your efficiency of this solution, while it's better than your traditional boilers, is still not good enough to make the cost of going to an electric solution on par with that of a natural gas solution. Electricity is more expensive than natural gas, we all know that. And so this option to decarbonize ends up creating an increase in cost for that customer. And ultimately, you, the person that buys that product. So if that's the case, why don't we figure out a way to improve that efficiency? So what we're doing at AtmosZero is instead of having an efficiency loss, instead of being less than 100% efficiency, we're creating twice the efficiency. So up to 200% efficient compared to electric resistant boilers. Sounds like magic, but it's really not. This is why heat pumps are awesome. I think that's why you're all in this room. It's because there's a completely different way of actually creating heat. I'll talk about how that works in just a minute. Any questions on this before we carry on? Cool. So, heat pumps are actually quite common. Who here has a heat pump? What kind of heat pump do you have, sir?
Refrigerator.
Great answer.
I would say the same thing about my air conditioning.
Air conditioning?
Yeah, air conditioning.
Air conditioning. Fantastic answers. Air conditioning, heating for residential applications, also automotive. Teslas actually have a lot of heat pumps in their cars for, electric ranges depend on energy consumption. If you can use a heat pump, decrease your energy consumption, you have a longer range. your refrigerator. Great answer. A lot of people don't recognize that everyone has a heat pump in the US, really. And what you're seeing is, this is not refrigerators, this is the heating application of heat pumps. You're starting to see a lot of residential type of heat pump adoption continue to grow. Those are international numbers. You're not seeing the same kind of adoption numbers for industrial settings. That's because the heat pumps that are out there for industrial applications cost too much to deploy. What we're doing is solving that with our solution. We're minimizing the capital required to deploy the solution so more people can deploy and start saving on CO2 immediately, right? Before we get into that, does everyone know how a heat pump works? I'm gonna go with a medium on that one. Okay, let's just talk through it because I don't want anyone to get lost in terms of how our system works. This is just a PowerPoint drawing. My PowerPoint skills are fantastic about how a heat pump, the basic cycle of this works. I'm gonna see if I can do this without tripping or hitting my head on something. Well, or unplugging something, which I might have just done. So, sorry. A heat pump based system is a closed loop of a refrigerant inside 3 or 4 different devices. Thank you for checking, or making sure I don't trip again. What we're doing here is we source heat from a certain location. Maybe a lot of you are familiar with air sourced heat pumps, and maybe they make hot water or something like that. They're pulling heat from ambient air. That air goes into an evaporator, which has liquid refrigerant coming in, and the heat from that heat source converts that liquid into a gas. So we absorb heat from a heat source, whether that's air or water or something else, and convert that liquid refrigerant into gas. That gas is then fed into a compressor, and we feed that compressor, in our case with electricity. Some other folks use heat to drive that compressor and take this gas from one temperature and pressure and compress it to a higher temperature and pressure. Now that you got that soup, like nice and warm and hot refrigerant gas, you send it through a condenser. So now you're going to transfer that heat that you just put into that with that compressor into something you want to make hotter. In our case, we're taking water and making that into steam. So we take that work that we just put in this gas to make it hot and transfer that heat out of that refrigerant gas into the water to make steam. And we use that steam to do something else with, right? So now the gas condenses, comes out as a medium temperature liquid out of the condenser, and the whole cycle repeats. And this is how you're effectively just moving heat. You're absorbing it from one place, putting it somewhere else. This is the reason that we can get efficiencies of over 100%, because we're not just converting 1 unit of electricity, thermalizing it into making heat. We're using 1 unit of electricity to drive a compressor, which then compresses and makes high temperature refrigerant. That's when you get the efficiency multipliers that we're talking about with heat pumps. So that's a metric that we call COP, or coefficient of performance. Residential applications, you can see pretty high COPs, 4 maybe. And in certain other applications, if you have to start from a really low temperature and make really, really hot stuff, that COP comes down because it's a big temperature lift, is what we call it. Any questions on this before I move on? Sweet, clear as mud, awesome. So that brings us to boiler 2.0. This is the AtmosZero system. And what I've got shown here is a sample kind of facility with our heat pump. And what's unique here is that we're an air source heat pump that you're probably used to in your application settings. But so we're pulling in heat from ambient air here, just like I showed in that evaporator in the bottom part of the cycle. Pulling that heat into our proprietary heat pump and upgrading that all the way from ambient conditions, which can be, today on a good day, it's like 15 Celsius, 60 Fahrenheit outside, all the way to 200 Celsius. That's that magical end point of that 50% of industrial heat needs, right? So this is process relevant steam that we're upgrading ambient air from. So that's a huge, huge lift. And we're enabling that with our AtmosZero system. And so there's a couple reasons why we're sourcing from air. But the key point here is this is meant to be deployed inside a facility or even outside. So this is the air coil, this is our heat pump. These can be collapsed and the entire system can sit outside. The whole point of that is to make a plug and play, easy to deploy solution so that we don't have to worry about a lot of facility modifications or integration challenges. When we talk to customers, that integration aspect ends up being a lot of challenges for folks to find a way to locate the system or to tie into existing systems and interfering with other processes, right? A lot of times when you're talking to, for example, pharmaceutical companies, they don't want to let you inside the facility. They've got proprietary processes that they want to keep with themselves. So having a system that can be collapsed and put outside fully and make steam and tie into the network, super enabling. And that's done because, again, we source our heat from ambient air. And that is a key point of there's no waste heat required. So another solution that kind of exists but isn't a large market yet because it's a challenge to integrate are waste heat driven heat pumps. That means instead of sourcing heat from ambient air, you have hot water or something like hot water you pull heat from and use that to upgrade to make steam. That is an inherently limiting factor, which I'll get into a little bit, but we're differentiating from that because now we want to create the most modular, easy to deploy system, and that's this. Any questions? So we are solving the two main barriers for decarbonizing steam for the industrial sector. We are making it operationally efficient. We are using a heat pump instead of electric resistant boilers. Twice as efficient, right? Keep that cost down. But also capital light. And that again goes back to the fact that we can create this as a standardized product. It is something that we can mass manufacture because it's standard and integrates the same exact way in all these different facilities because it's an air source system. The heat I need, I just get from outside. All I need to run this system is water, the same water you put in your boilers today, and electricity. I just plug it in and it goes. So we can standardize the design. It makes some amount of steam, and we can mass manufacture that, bring the cost down because now we have economies of scale, and we can integrate with our facility in a much faster way. So that keeps the cost of engineering or that customization very, very low. This is the enabling part of what AtmosZero is working on.
Excuse me.
Yeah.
Do you have any hybrid systems that can use waste heat?
Yeah, great question. Absolutely. We're not naive to this, and the reason is because, I'll get into that in a second. We can use waste heat systems to increase our performance if it's economically feasible.
Mm-hmm.
If you have to go and tear apart your entire facility to get that waste heat and then store it and then source from there, maybe the economics don't work out. We'll walk through that in the next couple slides actually, so great segue. So you might be asking, hey, if you're starting with, it gets cold in Fort Collins, what if it's 0 Celsius or Fahrenheit outside and you want to upgrade that all the way to 400 Fahrenheit? That's going to be a pretty big lift, that's going to be hard to do. So why don't you just start with something hotter? That's how thermodynamics works, right? And you're right. So in this case, I've got a few different options for decarbonizing steam. In this case, we're trying to make 1 megawatt of steam. So if you have an electric resistant boiler, you're consuming that much in terms of electrical. That's why it's expensive to run. If you have an air source system like AtmosZero system, and we have in ambient conditions like you're expecting in Fort Collins, we cut that consumption of electricity down by half. This is why we're operationally more efficient and more cost effective than an electric resistant boiler. But if you were to go from air sourced to something like a waste heat stream of 15 Celsius, 30 Celsius, all the way to 90, so the hotter and hotter this thing gets, the performance or the COP, the efficiency of this device continues to increase because now instead of having to go from 15 all the way to 200 Celsius, you're going from 90 Celsius to 200 Celsius. Efficiency improves. And so that's that blue chart here is that your electrical consumption comes down. What that means is your operational cost comes down. This makes sense. This is why a lot of folks are interested in waste heat recovery. The problem is you don't actually account for everything here. This is what I allude to with invisible costs. So this is what, when we talk to customers and other deployers, this is what they see as being a barrier to adoption. So electric boiler, this is the capital effectively to buy a boiler and plug it in. Electric boiler. Pretty simple, ready to go. Same thing with the air source system. It's a plug-and-play solution, ready to go. The waste heat-driven systems, the biggest challenge is you have to do a lot of customization per facility to go get that waste heat. If you've got a facility here, you got waste heat located over there, you now have to go deploy hardware, which requires engineering, to go get that waste heat, store it over here, and then use that waste heat to drive a waste heat-driven heat pump. Ends up being expensive for the engineering effort, the hardware to deploy that, but also the facility downtime. If you're trying to get waste heat from someplace, you gotta shut down the manufacturing to go get that waste heat. And so when you start looking at it, that ends up being roughly 3 to 6 times the capital cost of just the heat pump itself. And when you think about how many more millions that is, and you've got a company with multiple locations worldwide, this is not a scalable solution. If you have to do that custom engineering for each facility, and each facility looks different, that's going to be very expensive. The benefit, of course, is that this line shows you the operational cost. So your operational cost per year, in this example, comes down. This is the whole point of why you want waste heat. And this is what most people just see. They don't see that larger capital cost. Let me show you this in a different way. If I show you the rate of return, which means how long will it take you to pay back on the additional capital for a waste heat driven system as a function of temperature, compared to just an air source system. So these systems are more efficient than the air source, but they cost more to deploy. We're talking about 140 years on the high side for 15 Celsius, which is the most common source of waste heat. We're talking about 40 years of payback on like 30 Celsius. That comes down as you get to higher and higher quality waste heat, which makes sense. The problem is they're almost always longer than the lifetime of the equipment. So even though you might be better efficiency-wise, the amount of capital required to go and deploy these waste heat-driven systems won't pay for itself. There are some circumstances where they will, and that's totally fine. But when you start getting to these high-quality temperatures, that is very infrequent availability of waste heat. Usually you have batch processes, things that turn on and off, that might create this kind of temperature. If you're trying to create steady steam, always available steam, you can't rely on batch processes. So this now also becomes a challenge of availability, the temporal mismatch of when waste heat's available versus when steam's produced. This is again why we're focused on air source, because now we have a deployable solution that can run 24 hours a day. Oops, too many slides. Going back to it, this is everything I just mentioned in one slide. We don't have to read it. I just want you to focus on this. One product we can mass manufacture that can deploy in the United States, in the EU, in India, in Asia, etc. Only thing that changes is the power, the voltage, and the frequency. Everything else, for the most part, stays the same. We now have a mass manufacturable solution that can make steam from ambient air in all of these different locations. That's an enabling feature for folks that have multiple locations. AstraZeneca has 100 different manufacturing locations worldwide. They're not going to do a custom solution for every single one of them. They can, it's going to be expensive. This is making decarbonized steam available for the mass market. Any questions before I carry on? Yes?
So does it make sense to put these facilities in places where it's warmer all year?
Yeah, that's a great question. Absolutely, that helps. It's not required though. We're obviously in Fort Collins. I'll get into our first customer in just a little bit, but it's New Belgium. They're just down the street. It gets cold in Colorado. We're designing this system to run down to minus 4 Fahrenheit at full rated capacity. So anything lower than 4 Fahrenheit, we can either go with a hybrid system or even just derate our system a little bit or have a backup boiler. So absolutely, we recognize it's a global issue and globally there's cold areas. Good question. Anyone else? Am I going too fast? This is clear?
Yeah.
All right. I talk fast, I get excited. A little puppy over here. All right, so who here has heard of energy storage as a way of maybe decarbonizing heat? Antora, Rondo, those folks, those names start from there. Premise is this. Instead of using heat pumps, you can use clean electricity or cheap electricity when it's available and use it to create a bunch of heat and store that heat in some medium. Some folks use rocks, some folks use carbon graphite blocks, things like that. You want low-cost things. And then when you need that heat, you can dispatch it because now you create it at low energy cost. You can dispatch that heat to make either steam or hot air or whatever you want, right? Same kind of application space. Interesting concept, energy storage makes a lot of sense. You know, these things can get up to pretty high temperatures, 1500 Celsius. This goes back to, I forgot what asked the question, steel or those kind of application spaces. The challenge here is your efficiencies are always going to be lower than 100%. Always. Because you're always just creating one unit of heat, electric in, one unit of heat out. And the whole point here is to do arbitrage. So use electricity when it's low cost, and then create heat and dispatch that heat when you need it, when electricity might be more expensive. Problem is, when electricity is low cost, for them, electricity is low cost for me too. So I can continue to make steam at low cost. What they need to charge up this kind of energy storage device is, in an 8-hour window, for example, 4 times the power output in that 8-hour window to charge the entire system if you're trying to feed heat for the entire day. So your electrical interconnections, your electrical upgrades, the transformers, you might need a substation to give you the power to charge this stuff up when you need it. So it makes sense for certain temperature ranges. I'll talk about that in just a second. But in terms of making steam, this is going to be a costly approach. Case in point, what I'm showing you here, orange curves are heat pumps. This blue curve is energy storage. And what I'm doing is, even with extremely low cost of electricity, with very low cost of energy storage, because that efficiency is only 100% max, it will never compete with the heat pump below a certain point, where the efficiency advantage of a heat pump wins. And this is, in this case, an air source heat pump. So that temperature range, anything below 225, 250 degrees Celsius, the advantages of the heat pump being an efficiency multiplier will pay for itself, as opposed to the best case scenarios for energy storage. So anything above that, energy storage might start to make sense, especially at the really high temperature things where heat pumps may not be so good for. So we really look at these energy storage devices as complementary, but not overlapping in terms of applications. Cool? Cool. So ultimately what this means is, if you're consuming natural gas today in the US or the EU, and you want to decarbonize, you've got a couple options. Hydrogen is making a lot of news today. Hydrogen, I think, is great, but it doesn't really make sense to make steam out of hydrogen. It makes great for feedstock fuels or steel. And it's also really expensive and hard to find, hence the high cost of hydrogen compared to fossil assets today. Same thing with renewable natural gas. Great idea, you can have a drop-in fuel to use with your boiler assets instead of having to change all of that out. Hard to find, expensive too. Electric resistant boilers, this is what we're talking about, is like the de facto solution for folks trying to decarbonize today. And it's working for some folks, but it's expensive to run. What we're offering is a product that's less than half that cost. And that brings the cost in par with that of natural gas in the US and in the EU, creating a cost competitive way of decarbonizing with electrification. Technology over. We haven't even talked about how we're doing this stuff yet, right? All right, talk about too many slides. Same exact concept as we ran through earlier. It's a heat pump. We're sourcing from air. These are our air coils where we pull heat in from ambient conditions. Bring that to our evaporator. So this is the same exact heat pump cycle we just went through. Heat comes in here, turns a liquid refrigerant into gas. That gas gets compressed into high temperature pressure, rejects that heat from that compression process to something else, and then that cycle repeats. That something else is another heat pump cycle. So we have a cascaded system. We have 2 heat pump loops tied together. So as this gas is converting to a liquid, this liquid is turning to a gas. It's a dual phase change heat exchanger. And that lets you get the lift, the temperature from ambient air, all the way to steam temperatures. And the reason we split it is because instead of using one cycle, is that we can fine tune the thermodynamics now. There's not a good single refrigerant that has the best efficiency or commercial availability to go from here to here. By splitting it into 2, we can use one refrigerant here and a different one here with certain properties that are best suited for that temperature range. That gives us the best efficiency possible. So this is the simplified schematic. You'll see what you come up next door. It's a little more complex, but that's why we're here. And so this ultimately has hot refrigerant coming in here as a gas, converts liquid water into steam, and that steam ties right into the distribution header at the facility, the district steam network, whatever you're trying to decarbonize. So it's quite literally a plug-and-play solution. I'll show you how we're integrating this with New Belgium in just a few slides. I might, quick to scale, skip this one maybe.
Zach, can I ask you?
Yeah, sure. What's that?
What refrigerants are you using?
Yeah, so we're using just conventional refrigerants off the shelf. The specific ones I will not disclose here, but they are just standard HFOs that are extremely low GWP and low ozone depletion and low toxicity and low flammability, which means you could probably figure it out. Kigali compliant.
Yeah, I mean, low global warming is a little bit of a conundrum now, right?
In what sense?
Lower ones are coming, and you're probably not using the
So there's low ones already on the market. That's why the way that we've positioned this entire company is to put a product in the market in less than 3 years. That's a segue to this slide. But to do that, we're making sure we're not limited by our supply chain. So when we looked at what refrigerants we want to use, we wanted to find refrigerants we could buy today that we're not dependent on development of in the future. So our products that we're building have standard refrigerants that are commercially available.
Right, and I'm just wondering, so you're never gonna disclose this? I'm wondering, so I know that lower ones are, lower global warming refrigerants are coming. Can you tell me what global warming?
I will tell you that these are less than 100.
Less
So,
than 100? Okay,
so that's far lower than any sort of requirement you'll see.
okay,
And when I say lower than 100, I mean much lower than 100.
okay.
Yeah, we can talk offline about it though. Again, going to what my background was about focusing on commercialization, putting products in customer hands, and solving real world problems. That's what AtmosZero was designed to do. And the way we're doing it, and the reason that we started 2 years ago and have a full-scale system running next door and have a commercial partner that's going live next year, that's 3 years, is because we started at an at-scale system. We built it for industrial scale purposes. And so we're not starting small, having to learn and then scale it up and learn some more, and scale it up and learn some more. We started at the relevant scale and figure it out and learning our lessons and design challenges and controls opportunities at the industrial scale, and then taking that and making a product out of it. That's what's getting us into the market quickly, and we're leveraging CSU for this, of course, and the pace of their ability to build things, our expertise on turbo machinery, which is what we're using in our compressor technology, but also 90 to 95% of our components are available today. Kind of off the shelf, if you will. Same thing with your refrigerant question. Heat exchangers. We're not doing any custom design heat exchangers. We're buying those off the shelf. We're buying valves off the shelf. The kind of supplemental equipment. There's a few things we're creating and building ourselves. That's where our IP lies, and a lot of the enabling technology. But for the most part, these are technologies or parts that we can buy off the shelf and really speed ourselves up to market. Talk about what you're going to see. This is a CAD rendering, and this is what's actually in the facility. This is actually kind of an older photo, so it's not fully what you're going to see. It's much more fleshed out there. But I mentioned a cascaded system, right? So we've got a low temperature evaporator. There's a heat exchanger in this mess of a CAD drawing that sends low temperature refrigerant to a compressor on the low side. You'll see that next door. It's actually right here. Whoa. Wasn't me. That low temperature compressor sends high temperature gas to this two-phase heat exchanger. That's where that gas converts into liquid and uses that energy to evaporate the other side of the heat exchanger. That goes to our custom AtmosZero designed and built stage 1 to 2 high temperature compressor, and another one in series, stages 3 and 4, to get the temperature lift we need and the pressure ratio we need to be able to make steam out of water. So that then feeds what we call the hungry hippo, because to me it looks like a hippo. It's a kettle. It's a heat exchanger where we have refrigerant on one side and water on the other side, and we transfer heat from the refrigerant to water to make steam. We've been running this system since October of last year, so 6 months ago. Wow, 6 months ago, and things have just been cruising. We've been sitting at 150 Celsius output steam for like the last few weeks, just running steady, and just getting as much data, performance data, interrogating the system so we can take that back to our simulation models to make upgrades or understand the system better. What's up?
What flow rate of steam are you getting at 100?
Yeah, so we're about 1,800 pounds per hour, 1,750. We're targeting 2,200 as our full capacity per one of our units. So it's 650 kilowatts thermal is our heat duty. So when we go upstairs and over, you'll be able to see all this stuff. So this is the hungry hippo. We have a high temperature compressor here and here next door, low temperature compressor. And underneath it is just a bunch of the heat exchangers that transfer heat around, which actually I have a couple diagrams here that show you. We won't be able to see this because we're not going to get ground level, so we can see the economizers, suction line heat exchangers, those are underneath. But you'll certainly be able to see this guy that makes steam. Probably won't be able to see the evaporator, but you'll see the high temperature compressors from top. fundamentally the thermodynamics is all the same. It's that cascaded system.
What's the pressure of the steam?
We are making, what's 150 C is 60 PSI.
Yeah.
G. So all of that, it's kind of an exploded view. It's a deconstructed sandwich, but with a heat pump. It's not in a package-friendly type of thing that we're going to deploy to a customer. What we're deploying next year is what you see up here. So it's our pilot system that we're launching with New Belgium. So our heat pump lives in this part, and these are our air coils that we pull ambient heat from ambient air. We tie into electrical. We tie into we take feed water from their conditioning units, and we have a blowdown output from our system, and that all goes into making steam as an output, and that steam ties into their existing infrastructure. So it's as plug and play as you can get.
Can you just keep stacking these modules together? Can you say 3 megawatts of it?
Yep. So we're jumping ahead, but one of these units is about a third of the steam demand in New Belgium. So when we do a full steam replacement, we would tie in maybe 2, maybe 3 in parallel to get the flow rates that you need. Yep. Yeah, jumping ahead. First customer. So excited to talk about this. This isn't a secret. This is New Belgium. They are awesome partners. In fact, yesterday they did some crazy cool stuff with Earth Day. I'm not sure if you all saw that, but great partners because they're really walking this process with us. We are the missing link. Steam is a missing link for them to decarbonize and to do so cost effectively. And so we're excited about this going live in March of next year with that kind of configuration I showed you. We're making 165 C, and we're making that with 2,200 pounds of steam. So that's 1/3 of the steam demand. It's going to be a 6-month demonstration, pilot if you will. And then after that, doing a full steam replacement, not just at the Fort Collins location, but there are 3 other locations. They have a place in Kalamazoo, Michigan. They have a place in Asheville, North Carolina, and Daleville, Virginia. That's the beauty of having an air source system. It is a standardized product that integrates the same exact way in every single facility. If you've got 4 facilities and you're trying to decarbonize that, ends up being, and you're using a waste heat-driven system, for example, ends up being a lot more cost prohibitive, and you end up just taking a lot of time to deploy. An air source system can help you decarbonize like that. This is kind of public, but not really. Ignore the giant blue sections, that's not our project. But this is the exterior of New Belgium. This is where our system is going to be sited. So we've already started doing the site prep work to have our system fully located outside. So it is a skid-mounted system that sits on a concrete pad, plug in electrical, plug in water, make steam, tie that steam back into the building, you're done. So this is something that once we get it installed, you can actually go see it outside at their facility. It's right in the northern part of their building. So I'm super excited about this, and it shows just the modularity of our system.
What voltage and
Yeah.
power supply do you need?
Yeah, this is 480 volt, 3-phase. Very standard kind of things for industrial applications. And just to show you that there's other applications, so that was the food and beverage opportunity. This is district heat. So we actually have a case study related to this. If you are a university campus and you're trying to decarbonize, the main approach today is to take the steam network that you have that's underground for several miles, dig it all up, replace it with hot water systems. It's more efficient, so we're talking about a geothermal-based system. But to do that, it's 8 to 10 years of implementation because you have to dig up campus and you have to disrupt campus life. Better than that, it costs anywhere up to $500 million to $1 billion to do so. What I'm showing you here is the payback time frame if you go with that route compared to an air source steam generating heat pump. It'll take upwards of 400 years to pay back for that de-steaming event. That's why, not only that, so not only are we like 1/10 the cost, we're 1% of the time to deploy. Instead of 10 years, we can do this in a month. We just have systems that plug it in and you're ready to go. Not only that, we don't need to have a centralized steam plant anymore. Because we're a modular unit, we can have the steam producers closer to the buildings that end up needing steam. So all that transmission loss with steam networks, we can avoid that. Same thing applies to other industrial complexes, right? If you have steam that you're sending miles away, you can just make it on site closer to where you need to go and get higher efficiencies for that. So this is really fun. When I was at San Francisco a couple months ago talking to Campus Energy, the main thing everyone was talking about how they're ripping out the steam infrastructure, and I kept asking them, how's that going? I goes, oh, it's great. We've got engineering approval and all that stuff. I'm like, all right, so what's the holdup? Like, oh, we just can't seem to raise the money. Really? $500 million? You can't raise that kind of money? Come on. Yeah, so it's, to be fair, they didn't have this solution before. So this is an interesting talking piece when I'm talking to customers about how do we decarbonize campus in a more cost-effective way, and more importantly, in a much shorter time frame. So we're ready to scale for global impact. Lots of words here, but we started that off at scale so that we don't have to keep re-engineering and relearning. Every time you redesign something, you have to relearn how the system works. We're starting at scale to de-risk this technology so we can go to the market as fast as possible. We've also got a lot of supply chains that we're developing, key partners that are enabling the hardware we need to get to be able to launch our product next year. Of course, being here at CSU is fantastic. Joe in the back, I'm not sure if you've had a chance to meet Joe, but he's one of the main reasons that we're able to do the things we need to do at the pace that we're doing it. I haven't met someone that can keep up with us until I met Joe. So thank you, Joe, for making sure that we're able to run our system next door and get the data that we need. And of course, this is a global problem, right? So we also have a subsidiary in the EU. We're based in the Netherlands. We actually have a couple other customers that we're not publicly talking about, but now this will be on YouTube, so we're kind of publicly talking about it. We have customers in the EU that need a heat pump-based solution that we're scaling our system to manufacture and deploy to. Again, that standardized product looks the same, it works the same way everywhere you go, and integrates in your facility the same way. So we have broad applicability with our technology. That's it? Did I put, wow, an hour, really? I will stop talking and see if there's any more questions. Yes?
How big is one of those modules physically?
Oh yeah, that's a great point. The width of it is 8 feet wide by 20 feet long. So roughly like a standard container size. And when you get to industrial scale things, that's normal. It's a normal unit of measurement.
Yeah.
One container.
Handy for shipping.
Yeah, exactly.
Do you have to space a certain amount of part you're putting several parallels so you get enough airflow?
That's exactly right. Yep. Yep. But it's not like this significant. It's got to be a mile apart from each other. It's just like I think roughly. I'm not going to say this off the cuff, but a few feet. Yes.
Any consideration of the company, I think phase 2, to look at heat geotechnic wells from, for example, reutilize oil wells, lower temperature geotechnic?
Yeah, so absolutely. The source that we pull our heat from, it could be air. It can be waste heat or geothermal-based solutions. It just really depends on the geographic limitations, right? So we get asked all the time about geothermal sources of heat, and I'm like, yeah, it's great. So it's a hotter source and it's more consistent, but now you got to drill a well, so that's capital that you have to worry about, and it's also location specific. Are you going to drill a geothermal well in New York City? Probably not. So there's limitations on that too. But absolutely, we can use that kind of resource to improve our efficiencies. Yeah.
So you said your system is designed to operate down to +4 degrees Fahrenheit.
-4.
-4 degrees Fahrenheit. I think that's the design temperature right here in Fort Collins, right? Something like that.
About right, yeah.
And is it? And what's your COP at that temperature?
Oh man, off the top of my head, I don't know. But in general, what we say is an average year is about 60 Fahrenheit. And then if we're making 150 C steam, 60 psi steam outside, or for process conditions, we're targeting a COP or efficiency of 2, so 200% efficient.
Oh, so over that entire temperature range.
From sourcing from
So
60 Fahrenheit.
an average of 2
Yes.
over the year.
Over the year, exactly. So when it's cold outside, the performance will be lower. But then when it gets warmer outside, your performance will be higher.
Yeah,
Averages it out to be 2.
but probably at -4, your COP is less than 1.
No, that's not.
Is
We're,
it
we're,
one?
we're, we're
Is it
significantly
above
higher than 1.
Is it above 1?
Oh yeah, it's above 1. The break even, if I remember correctly, is minus 40 Celsius is about when we get to COP of 1. What that is in Fahrenheit?
-40.
Minus 40 is the same.
Oh, you're right. So what that is minus 40 in Fahrenheit. YouTube, thank you.
Okay.
Yeah, so that's about our break even for COP.
So, New Belgium, their process is continuous. Can they decide not to make beer for a little while? Or,
I hope not.
but they could operate at any, even during polar vortex.
Right. Yes.
At a COP that was not the same electric.
That's right. And so what's nice about our system and unique as well is that we run in parallel with their existing systems. So, for example, if it's really, really cold and we can't operate, maybe it's 2 days a year, we can just run in parallel with their natural gas boilers that they already have. And so they can kick that on for those couple days, or I can have an electric resistant boiler that kicks on for a couple days, and then for the rest of the time, they're running at higher efficiencies. That's what I mean by a hybrid approach to decarbonizing steam.
So are they going to keep gas?
Yeah, so for the pilot, for sure, they're going to keep their natural gas boilers as redundancy, and we're only replacing 1/3 of the steam demand anyway, so some of their boilers are going to be operational. But when we get to like the full steam replacement, you always want some sort of redundancy in steam. Even right now, they have two boilers of redundancy, just in case if you go down. If you lose steam, you lose production. You don't want to lose steam. That's why you always have redundant systems.
So they may keep natural gas. They probably will keep natural gas.
Yeah, but if you don't use it, it's not so big a deal.
Probably cost more to decommission than.
Yeah,
we just-
it's extremely cheap insurance.
Any thoughts of a smaller system for, let's say, a 10-barrel brewery, microbrewery?
Yeah, it's funny you ask that because all I get asked for day in and day out are larger systems. So, to be honest, like what these kinds of technologies work best at is continuous operation. And when you get down to like the more craft brewer type things where they're not always producing beer and you turn the system on and off, you don't get your value out of it. So we don't want to get too much smaller. We want to have systems that you run continuously all year round.
Makes sense.
But I've gotten asked a lot of that too.
I've been, business-wise, I've been led to understand that a lot of the companies that do chemical processing, especially through northern Germany, are starting to move to the U.S. because of natural gas prices and that thing that's going on out there in
Yeah.
Russia.
Yeah.
Are you able to get in contact with people? I know BASF is relocating. A lot of those have been able to talk to because they're going to rebuild from the ground up. Any positive? I'm not asking for details, but I've been able to get in on any of that relocation work.
Yeah, it's a great question. We talk to customers day in and day out. Certainly Europe is, and the reason that we're in Europe is so we can give them an option to help reduce their operational costs, but also to increase the energy resilience. The war in Ukraine is certainly one of those things that happened that spiked natural gas prices a couple years ago, shut down a lot of facilities, or ended up having folks to relocate for that reason.
Yeah.
By going this solution, you don't need to do that. So we do talk to those kinds of folks that are under that kind of pressure, but also under the pressure to decarbonize. What's been crazy, 20 years in this world, not in this world, I wasn't born 20 years ago. Thank you, lots of gray hair. 20 years in this climate tech experience, this is the most momentum I've seen on the decarbonizing front. Sponsored, of course, by things like the IRA, the Department of Energy funding, just putting lots of money out to support these technologies, but also commitments from companies that are standing. Like, a lot of companies worldwide are wanting to decarbonize their process without any sort of federal incentives. Does it help? Absolutely. But people are making this come true. That's why you're seeing electric resistant boilers going out the door. That's the only solution folks have, and they're selling them even though it's increasing the operational cost. So, absolutely, but like, yeah, I mean, there's a lot of companies out there that need steam, right? 12% of global CO2. Love if you have connections with folks that need some help. Love to have that. Sound good? Yeah.
I'm not sure how to ask this, but how quick, you're doing this pilot project, it'll be like 3 years, right? And how quickly do you anticipate being to be like really mass production, like really crank them out?
Great question. The pilot project's 6 months.
Okay.
We're going to be, so we are setting up our own manufacturing facility to where we'll start putting units out for sale starting in mid to late 2026. So we've got a number of customers doing kind of early sales, early deployments, but like the come to our website, buy a product, that's 2026. And then that's scaling quite rapidly to be hundreds of units shortly thereafter per year. Into the 2030s when we'll be talking about thousands of units per year.
Awesome.
Exciting times.
Yeah.
Just in general, have you run into any maintenance issues? Like heat exchangers are kind of notorious for pipe fouling and build up. I know the water quality here in Colorado is really good, but the rest of the country's not so great.
Yeah.
So how's maintenance on the
Yeah.
systems you have?
So that water quality question, I mentioned it, but we're using the same water that you're feeding your boilers today. So generally that comes with some sort of water softening, some sort of deaeration to help minimize fouling issues on the heat exchangers. On the refrigerant side, nothing yet. We're planning around a standard like annual maintenance, just like most facilities have, shut down for like a couple days to do heat exchanger cleaning, things like that. That's what we're basing our maintenance schedule around. But we're going to learn more and more as we continue to test further and have more products out in the field.
I think you said that you have been talking about your sweet spot being continuous use of steam. What about what about boiler plants and buildings? There are still some. Is that something that you would go after, where say they use it heavily during, for maybe 6 months of the year, and there's a shoulder season, and they might not use it at all in the summer?
Yeah.
Or is that, do you foresee that just not being cost effective?
It's actually a great market still, because that kind of speaks to what we talked about with the campus energy type of thing.
Yeah.
When you're still comparing to hundreds of millions of dollars to rip that out and replace it with a hydronic system, it still makes sense to be able to deploy our solution and be able to provide that easy. You can also drive chillers with steam. So if you need to provide air conditioning or cooling, you can still use that steam for something else. Same thing applies to New York. You've got these massive office buildings and multifamily houses, buildings. To gut that and replace it with a hot water system is almost unfeasible because of the disruption to the tenants. You likely have to get them out of the building to do so. And so if you can't do that, and you have local law 97 starting to implement fees for folks that are non-compliant that still have natural gas boilers, you're gonna have to make a solution pretty soon. And right now it's electric resistant.
Yeah. Very interesting.
Could you repeat what your output power, thermal output power is, and what electrical input power you need?
Yeah, so 650 kilowatts of thermal output, and if you cut that by half, if we have a COP of 2, it's 225.
But that's average, so you probably recommend 400?
Oh, I see. What we say is, if you plan for a short circuit current rating of 1,000 amps, won't need it, but that's short circuit current rating, that would be more than enough, more than sufficient.
Okay. Thank you.
Good question. And that's a 480 volt 3-phase. Yep.
What would you say is your greatest impediment to doing all this more quickly?
All this work with what?
Doing all of what you're doing more quickly. Or getting to market sooner, ramping up sooner.
I ask my team that question all the time because I'm like, I need to. Time. There's only so much money can get you in terms of, can we throw more money at this problem to make it go faster? Sometimes yes, sometimes no. We just need to get things built and tested and better verified. We're doing that today. We're going as fast as we possibly can to get products out the door. I've been in hardware my entire life. To have something that goes out the door as a product in 3 years is unheard of. I'm not talking about a phone here. I'm talking about industrial scale, giant equipment. When you see it, you'll be like, oh, wow, we built what you see next door in 14 months. We designed it and built it in 14 months.
Incredible.
That's remarkable.
Are you aware of any competition from the large HVAC system manufacturers like the Carrier and Train?
Sure.
Developing things like this? I mean, it's not to denigrate at all what you're doing, but it's not super crazy, technology that's that cutting edge, right? The scale is different than anything I've heard of.
Yeah, sure.
Are the big boys in development and stuff like this?
Absolutely. What you'll generally see what these folks are working on are air source to hot water. And then what you might see in Europe is actually waste heat to steam, but that's really low pressure steam. Again, there's not this like air all the way to steam. This modular drop-in solution that can decarbonize processes in a plug-and-play solution.
So as far as you know, that's kind of your niche. There's no one that you're aware of competing with that.
That's right.
Yeah.
Is the competition getting hotter? Steam joke. It is, but we've got IP, we've got a product that's about to be out the door. I'm never going to say never. There's certainly folks that are out there doing great work that you see making steam generating heat pumps today, usually at a much larger scale. And the size that we're working on, 65% of industrial facilities are less than 10 megawatts of heat load, and most of what the big guys are working on are 10 megawatts plus of steam generating heat pumps. So it's hard to satisfy the majority of the load when your heat pump can't get that low.
For your proprietary components, where are they manufactured currently?
Yeah, we make them. We have some suppliers that make maybe some components, but we assemble all of it ourselves.
Who's so it's a U.S. built product?
Yes. Yeah. There's some components we source from overseas, but the majority of the components are U.S. Let's tie up the presentation part here.